In this video, we introduce a completely new way of determining stability of nonlinear dynamical systems, and it's called Lyapunov stability. So as we talk about the theoretical part of this, this is the example that you can kind of have in the back of your mind. And it's this idea that if you have this ball rolling in this trough, this valley, that we know that this valley, especially if there is going to be some element of friction on this ball interacting with this hill or this valley, that it will eventually rock its way down to this final resting position, and that's its equilibrium position. And so it's very intuitive looking at this. And what Lyapunov theory does is it kind of put this in mathematical framework. And one of the ways to kind of see this is the fact that the motion of this ball is always kind of down towards this equilibrium, in the sense that if you look at the direction of motion and the sign of the slope of this function, this green function, it's always going to be negative. Okay, and so that's this insight that you can keep in mind as we go through here. Here, the motion is going this way, and the slope is, so the motion in this case is negative, and the slope is positive. In this case, the direction is positive, and the slope is negative. So continuing with this same kind of example, consider that we have some sort of mass particle that has some sort of dissipative force, just like we were talking about, like a frictional force. In that case, we'd write the force is equal to this drag force here, where B is some positive parameter. And if we wanted to, we could rewrite this in terms of the velocity as V. And so that just gives that mv dot is equal to this drag force. And so we look at this, and it's clear that V equals 0, which is x equal to 0. This is an equilibrium point. That's where the mass is not moving. And so what we're going to do is we're going to pick a function and try to essentially build a function that does what we saw on the previous slide. So in this case, we're going to choose the kinetic energy of this particle. And in fact, Lyapunov theory is really kind of a generalization of an energy. So in a physical problem like this, it makes a lot of sense to pick something like kinetic energy. So notice this kinetic energy term, m is the mass, and so v squared is always positive, so which means that this energy is always either greater than or equal to 0. And it's only 0 if v is equal to 0. So now we'll take a look at what happens along this function e. What happens in terms of this dynamic? So what we do is we take the derivative of this function, the time derivative of this function e, and that means that we're going to take the derivative of this quantity, again the time derivative. So this uses the chain rule, essentially mv squared. The squared comes down, cancels with the 1/2, and we have mv, and then we take the derivative of v and we get v dot. So essentially this is dE dV dotted with dV dt. All right, and so this is dV dt, and this is dE dV. And so if we substitute now in what v dot is minus b, so v dot is minus b over m times v, but when you substitute in, the m's cancel and you're just left with this term. Again, v squared is positive, which makes that overall term negative. So e being positive, or 0, and its derivative, time derivative always being less than 0, means, so if it's always positive, positive or 0, and it's decreasing in time, then that means that eventually e is going to go to 0. So that function is going to go to 0, which means that e goes to 0. That means that v, in fact, goes to 0. And that tells us that this equilibrium is indeed stable. All right, and so that now we didn't use eigenvalues, but we're still able to show stability. And this is a kind of specific example, but really does show the basic working of Lyapunov theory. So at a more abstract level, the goal here is to pick a scalar function. So it means it's a function that outputs just a number, and it's going to always be positive or zero, so non-negative. And the key thing is that it's going to be decreasing along the trajectories of the system x dot is equal to f of x. And so now we're keeping this quite general. We have this non-negative function v of x, and what we want it to do is show that it decreases along trajectories that are described by this f of x. So if we want to do that, we're going to essentially, again, just take the time derivative of v. So v dot is just all the different states xi. We're going to do the chain rule. So it's dv dxi and then xi dt, which is this term. That allows us to substitute in and put in f instead. And so this is the sum over I. These terms each have I, and this term each has I. And so that is the same thing as the gradient of v dotted with the vector valued function f. So remember, the gradient of v is simply just the vector that has all of the partial derivatives with respect to the different states. So dv dx1 through dv curly dxn. So however many states there are, all those derivatives in a vector. And so when we dot it with the dynamics vector f, that gives us the quantity that we want. And what we want to do is we want to show that this is always decreasing. Because what ends up happening is, if we think about this gradient vector, this actually points perpendicular, by definition, points perpendicular to the level sets of v. So if this green function here is v, then each of these circles or ellipses ends up becoming the level sets of v. And so this figure here on the right should look quite similar to something we saw in the previous class. And so the gradient is always going to point out because v is increasing as x gets bigger. So v of x is always pointing out directly away. And now the question is if this quantity, v dot, is going to be negative, that means that v of x is going to have to be pointing kind of in the opposite direction. And so it doesn't have to point exactly in this opposite direction, but it needs to make sure that when you take the projection of this vector x onto the line through gradient of v here, that this projection, so this is the projection here, the projection points in the opposite direction. And so that is what it means for this to be negative. So it's going to be 0, this quantity is going to be 0 if they're actually perpendicular, and then it's going to be positive if f also points outside the circle or ellipse of the level sets. So this is kind of the geometric interpretation of what's going on, but it's really just the generalization that if the dynamics is pointing inward, is always pointing inward, then that means that the system is moving its way in here. And so if you keep doing that, keep making these level sets, it shows that you're going to get closer and closer to your equilibrium, or in this case, the equilibrium is at 0. So to formalize what it means to be stable in the sense of Lyapunov, it says that if we have some equilibrium point, x star, and this v of x is a continuously differentiable function, and we require these two things. So we require that v, this function, is positive for all x not equal to 0, or in this case, the equilibrium point, and that it can only be 0 at the equilibrium point itself. And then the second part of this is that the derivative needs to be decreasing or at least stagnant. So it needs to be less than or equal to 0. So if that's all true, then we can say that this equilibrium is stable. We can make this a little bit sharper. We have two further kind of corollary results, which says that we can replace this element here, number 2, we can replace that with a strict equality. Oops, not an under. This is a box, not a underline there. So that's not equality. So this is a strict inequality, and that means that if the v dot is always less than 0, then we can say something a little bit stronger, which says that we can actually say that this is asymptotically stable. We can come back one more time and make that a little bit sharper and say that, okay, well, we can go back and relax and say that we can have equality as well as less, so we can have v dot less than or equal to 0. But if we can also say that v dot is only 0 at the equilibrium point, then we can still say asymptotically stable. All right, so it's the chain of thoughts here. So we have this main result and then two corollaries that sharpen it. So let's just see a few examples. So if we have this simple dynamical system, x dot is equal to minus x. If we were to pick, again, we get to pick this, but again, there are many choices, but oftentimes you start with the simplest and see if it works. There are many that will work. So x squared is non-negative, so it's always positive as long as x is not 0. And then if we look at the derivative of that function along the trajectory, then we get the derivative of this x squared is just 2x x dot. We substitute x dot being minus x, and so then we get back this quantity. X squared is always positive, which makes minus x squared always negative. And so that means that this equilibrium point, x is equal to 0, is asymptotically stable. Here's another more abstract example. So if we just say that x dot, the dynamics is given by some function g, where g has certain properties. So g goes through the origin, and that the product x times g of x is always positive. So this is one way of essentially explaining that this is a odd function, or in the sense that it is in the negative quadrant in this third quadrant here, and then it goes up into the first quadrant here. And so that kind of function satisfies this inequality. So if we try again our quadratic function, then we take the derivative of that function to get v dot. So we get x dot. We substitute x dot in, which is just minus g of x. And so we get minus x times g of x. If we look at this, this tells us that it's always positive. So with this minus sign, it makes that always negative. So that again is asymptotically stable. Let's return and take a look at our example that we saw from the previous slides, where we looked at a pendulum. And if you recall, what we found is that without damping, we had an equilibrium at the origin and at every even pi multiples that was essentially a center. And so it's difficult to understand what that stability is because it's not a hyperbolic equilibrium. So it didn't fall within the class of equilibriums that we could use for stability. Once we had damping involved, then we could say that this was a stable focus, and that automatically gave us asymptotic stability. So let's see what Lyapunov theory tells us. So with friction, we have this dissipating term. Without friction, which is what we're going to look at, we have this dynamics equation. If we come up with a Lyapunov equation or a function, again, we might consider the energies of the system. So in this case, both play a role. So we can have both kinetic and potential energy involved here. And so if we pick this as our Lyapunov function, we take the time derivative here. And the only time, so L is not time dependent, that's the length of the pendulum. Theta is the only time dependent quantity, so we get this term by taking the time derivative of the first term, and then we get sine of theta from the cosine theta here, and then we get theta dot. And from here now, we go ahead and substitute in the quantities of theta double dot to get the dynamics. So we solve for theta double dot and put that in, and that provides us with this sine of theta here. And so what we're interested in doing is showing whether or not this tells us stability. And so what this tells us here is the fact that this E dot term, our Lyapunov function derivative, is exactly equal to 0. And so we cannot say that it's asymptotically stable, but we can say that it is stable near our equilibrium x1 is equal to 0, x2 is equal to 0. So when around that equilibrium, this is indeed this derivative is indeed equal to 0, so it's not less than 0 like what we had before, but at least it's 0, and that gives us the fact that it is at least stable. And so this corresponds to this idea that the dynamics actually points along the level sets of E. And if you remember, if you flip back to the previous slide, remember we have these concentric rings essentially, and what this is telling us is that this is actually we are picking exactly those as our Lyapunov function. Those are the level sets of our Lyapunov function. If we were to add friction involved, then the E dot term would have this quadratic term in terms of the angular velocity, and with the minus sign, which would then imply that not only is it stable, but it's also asymptotically stable. And so one really important thing to remember when you're using Lyapunov theory is the fact that it's excellent, very efficient. The only problem is you have to pick that function. And so in everything you've seen here and everything you probably will see in this class make for relatively easy Lyapunov function choices. But sometimes when you're working with real problems, that can be quite a challenge.